Everyone knows what the Big Bang is. That part is settled. The universe began approximately 13.8 billion years ago from a single point of infinite density, expanded outward in an instant, and everything, matter, energy, space, time, emerged from that one primordial event. This is not a theory on the fringes. This is the headline answer in every physics textbook on the planet. It has been tested. It has been confirmed by decades of observation, satellite data, and the slow cosmic drift of galaxies, moving away from each other at measurable speeds. The Big Bang is cosmology's greatest achievement, a triumph of human reasoning that reaches all the way back to the moment of creation itself. Except it doesn't. There is a crack in this story that has been widening quietly for decades. It does not appear in the summary versions. It doesn't make it onto the classroom posters or the television documentaries where telescopes sweep dramatically across star fields, while a narrator explains the universe's origin with practiced confidence. The crack lives in the equations, in the place where those equations are asked to do the one thing they were built to do: describe the beginning. And at that exact moment, in the precise instant the Big Bang actually occurred, the mathematics of modern physics does not produce an answer. It produces a breakdown. The equations do not simplify at the moment of creation. They don't approximate. They return something called a singularity, a point where every measurable quantity simultaneously becomes infinite and therefore physically meaningless. Temperature, infinite. Density, infinite. Spacetime curvature, infinite. The numbers stop describing reality and start describing a wall that every attempt to calculate through has shattered against. For over a century, theoretical physics has managed to describe the behavior of stars dying at the center of galaxies. The quantum behavior of particles smaller than any instrument can directly observe. The warping of time near massive objects, the expansion rate of space itself across billions of light years, all of it precisely, all of it elegantly, except the moment the whole story begins. That moment is silent. The silence is not an oversight. It is not a gap that more funding or a better telescope will close. It is a structural impossibility built into the mathematical framework that is supposed to explain it. Einstein's general relativity, the theory that describes gravity and spacetime at cosmic scales, breaks down completely at the singularity. Quantum mechanics, the theory that governs the behavior of the very small, also has no language for what happens at that point. For 60 years, physicists have known that a complete theory of physics would require both of these frameworks to work together. And for 60 years, every attempt to unite them has either failed or produced results so strange that their authors have hesitated to publish. The theory of everything that would explain the beginning of everything does not yet exist, and the Big Bang cannot be described without it. This should be the most famous problem in science. Instead, it is surprisingly quiet in the rooms where most people receive their understanding of the universe. Here is what the public version of the Big Bang story does not include. Physicists don't actually know what caused it. They know it happened. The evidence for the expansion of the universe is overwhelming and is not in serious dispute. But the cause, the mechanism, the reason an infinitely dense point of everything that exists suddenly began expanding rather than remaining as it was, has no physical explanation within current theory. Every model that attempts to describe the moment before the expansion either assumes the beginning as a given or eliminates before entirely by redefining time as a quantity that simply did not exist prior to the event. Both of these moves are mathematically defensible. Neither of them is an explanation. They are descriptions of the boundary. The boundary itself remains untouched. What physicists have instead are theories, not one. 8 significant ones, each built by serious researchers working at serious institutions, each attempting to fill the silence left by the singularity. And what is remarkable about these theories is not that they are speculative. What is remarkable is that each one, in the process of attempting to explain the Big Bang, introduces a new impossibility, a new strangeness that is more unsettling than the problem it was designed to solve. The more carefully physicists have looked at the origin of the universe, the less it resembles the clean, triumphant beginning that the textbooks describe. Some of these theories suggest the Big Bang was not a beginning at all, but a transition from something that came before, raising the question of what that something was and whether it too required a beginning. Others propose that our entire universe is an event that occurred inside a larger structure, which itself would require an origin. Several of the most mathematically rigorous frameworks predict that the universe we observe is only one of an effectively infinite number of universes, a consequence so radical that even its proponents struggle with what it would mean if true. One framework, developed from attempting to unify quantum mechanics with gravity, implies that time itself may not be fundamental, that time might be an emergent property of a universe that at the deepest level of its description is entirely static. No motion, no change, no before or after. Just a mathematical structure that contains within itself every moment that has ever occurred or ever will. These are not the ideas of outsiders. They are the ideas of physicists who have spent careers on the hardest problems in theoretical science and arrived at conclusions that should, by any reasonable standard, be more alarming than they are. The Big Bang is real. The universe expanded from an extremely hot, dense state. That is not what is in question here. What is in question is something quieter and more fundamental, whether the Big Bang was a beginning at all, or whether it was simply the edge of what our current tools are capable of seeing. Whether the confidence with which cosmology presents the origin of everything is proportional to what cosmology actually knows about that origin, and whether the silence around these 8 theories, each one built from legitimate physics, each one pointing toward a universe stranger and more uncertain than the popular story admits, is itself a kind of answer. Because here is what becomes clear when you follow these theories far enough. The more precisely physicists have tried to describe the moment reality appeared, the more convinced many of them have become that reality did not simply appear, that there is something behind the Big Bang that the equations are refusing to show, something the singularity is hiding. And the reason this matters, the reason this has shifted from an academic puzzle to a source of genuine unease among researchers who have spent careers working at the edge of what is knowable, is that the alternatives are not reassuring. They are not simpler. Every theory that attempts to reach behind the Big Bang arrives somewhere that raises a new and deeper version of the original question. Not what caused the expansion, but what kind of thing the universe actually is, and whether the tools that built the question are capable of surviving the answer. That is where this begins, not with certainty, with a crack. The Big Bang happened. That much is not in dispute. The universe was once unimaginably hot and dense. It expanded, it cooled, and over billions of years it produced stars, galaxies, planets, and eventually something capable of asking where it all came from. The evidence for this sequence is not ambiguous. The cosmic microwave background radiation, the faint afterglow of the early universe still detectable in every direction of the sky, confirms it. The measured abundance of hydrogen and helium formed in the first minutes confirms it. The observed recession of galaxies in every direction confirms it. The Big Bang is not a hypothesis awaiting verification. It is a documented feature of the universe we inhabit. What is disputed, quietly, carefully, in papers and conferences that rarely make it into public conversation, is whether the Big Bang was the beginning of everything or simply the beginning of this. The distinction sounds small. It is not. For most of the 20th century, the question was considered settled by default. The universe was expanding. Run the expansion backward and you arrive at a single point. Before that point, there is no space, no time, no matter, no energy, nothing the word before can meaningfully attach to. The beginning was not just a feature of the universe, it was the universe's first and most fundamental fact. Time itself started there. To ask what came before the Big Bang was, in this view, like asking what is north of the North Pole. The question dissolves on contact with its own terms. Then the mathematics started producing something uncomfortable. It began not with exotic speculation, but with a straightforward problem. The equations governing the very large and the equations governing the very small were both being pushed closer to the moment of origin, and what they returned consistently was not a clean wall, but a suggestion. A formal hint buried in the structure of the mathematics that the singularity did not have to be treated as a terminus, that it might, under certain conditions, be treated as a junction, not an endpoint, a transition. The difference between a wall and a door is not obvious from the equations alone, but several physicists, working from completely different theoretical frameworks, began arriving at the same unsettling conclusion. The mathematics did not require the Big Bang to be first. The cyclic universe model emerged from this recognition. Its premise is straightforward enough to state and strange enough to spend a lifetime thinking about. The universe does not begin. It does not end. It contracts, reaches a maximum density sometimes called the Big Crunch, and then bounces, expanding again, producing what appears from the inside to be a new Big Bang, but is from a wider perspective simply the next oscillation of a system with no origin point. Each cycle produces a universe. Stars form, burn out, collapse. Galaxies drift apart, matter disperses, entropy increases. Then the cycle closes. Then it begins again. The Big Bang that produced everything we have ever observed or ever will observe was not the first. It was not special. It was one beat in a rhythm that has no first beat. The immediate objection is thermodynamic. Each cycle should accumulate entropy, disorder, from the previous one. A bouncing universe would inherit the disorder of its predecessor and pass more disorder to its successor. Run enough cycles, and the system becomes too disordered to produce structure. Stars stop forming, galaxies stop coalescing. The universe becomes, in each successive cycle, less capable of producing complexity. If the cyclic model were literally true in this form, we would expect to find ourselves in a universe far more disordered than the one we actually inhabit. The objection is serious. It held the cyclic model in suspension for decades. Then Roger Penrose made a different argument. Penrose is not a marginal figure. He is a mathematical physicist who shared the Nobel Prize for his work on black holes and whose contributions to the mathematical structure of spacetime are foundational to modern cosmology. His conformal cyclic cosmology is not a casual proposal. It is a precise mathematical framework, and what it argues is this: the thermodynamic objection fails because it misunderstands what survives between cycles. In Penrose's model, entropy does not accumulate in a way that degrades successive universes. Instead, the far future of one universe, a state of maximum expansion where matter has essentially dissolved and only massless particles remain, is mathematically identical, in terms of its geometric structure, to the state of a universe just after a Big Bang. Not similar, identical. The geometry of an ending universe and the geometry of a beginning universe, at the right level of mathematical description, are the same geometry. This means the boundary between one cycle and the next is not a wall, not a singularity in the catastrophic sense, but a smooth mathematical transition. The end of one universe is the beginning of the next, without any discontinuity that physics is required to explain. One cycle flows into another, not through a violent bounce, but through a quiet geometric handoff. And what passes through that handoff? What links the outgoing universe to the incoming one? Are, in Penrose's framework, gravitational wave imprints, signals from the previous cycle, encoded in the cosmic microwave background of the next one as faint, concentric rings of varying temperature. Penrose and his colleagues searched for those rings. In 2010, they announced they had found evidence of them in existing CMB data. The result was contested immediately. Other cosmologists argued the patterns were statistical artifacts rather than genuine signals, that the analysis method inflated their significance, that the rings could arise from random noise. The debate has not fully resolved. The concentric ring signatures remain present in the data. Whether they represent genuine cross-cycle imprints or an artifact of the analysis continues to divide specialists. What is not in dispute is that a physicist of Penrose's standing built a mathematically coherent framework in which the Big Bang is not the beginning of the universe, but a recurring event in a sequence with no beginning, and then found what might be observational evidence for it embedded in the oldest light we can detect. The implications of this, taken seriously, are almost impossible to hold in the mind steadily. If the cyclic model is correct in any of its forms, then every event that has occurred in this universe has occurred before. Not approximately, not in some loose metaphorical sense, in the sense that the physical conditions that produce this particular galaxy, this particular star, this particular arrangement of matter on this particular planet have been produced before, in a previous cycle, with different specifics but identical underlying physics, and will be produced again. History, not human history, but cosmic history, the entire sequence of cause and effect extending from the Big Bang to whatever final state this universe reaches, is not a single line with a beginning and an end. It is a loop, one iteration of a process that iterates indefinitely in both directions without ever having started and without ever finally stopping. Nothing is new. Nothing is unprecedented. The first star that ever ignited in this universe was not the first. The formation of every galaxy is a repetition. The question of what existed before the Big Bang resolves, not into nothing, but into a previous universe. And behind that another, and behind that another, in a regression that the framework explicitly removes any reason to terminate. This is not philosophically neutral. The concept of a genuine beginning, of a moment when something came from nothing, when existence appeared for the first time, is foundational not just to religion, but to the intuitive structure of how humans understand causality, significance, and meaning. A universe with a true beginning has a direction. It is going somewhere. The beginning implies a trajectory from nothing toward something. A cyclic universe has no such direction. It is a system at equilibrium with itself, producing the appearance of history without history in any ultimate sense. Every civilization that has ever existed or will exist in any cycle is a temporary pattern in an eternal repetition. Nothing that happens within a cycle is final. Nothing is singular. Everything is, in the deepest sense available to physics, a recurrence. There is another framework, related in spirit though different in mechanism, that arrives at a similar destination from a different direction. Eternal inflation, originally developed by physicists Alan Guth and Andre Linde to solve specific problems with the standard Big Bang model, proposes that the universe is not a single bubble of expanded spacetime, but a region within a larger, eternally inflating medium. In this picture, the inflation that supposedly characterized the first instance of the Big Bang never stopped. It is still occurring in regions of spacetime beyond our observational horizon, and it is continuously generating new bubbles of expanded spacetime that each develop into universes with potentially different physical constants. Our universe is one bubble. The process that produced it produced others before it, and is producing others now. The Big Bang was local. The medium in which it occurred had no beginning. The formal structure of eternal inflation also produces an uncomfortable consequence for the cyclic picture. If inflation is eternal in both directions, if it has always been occurring and always will be, then the question of an initial state disappears entirely. There is no moment the process started. There is no first universe. The regression behind the Big Bang does not terminate at a creator state. It terminates at a process that is, by the equations that describe it, simply ongoing, with no origin required. This is where the mathematics begins to feel less like a description and more like a verdict. The universe we observe did not have to have a beginning. Several mathematically consistent, observationally motivated frameworks describe a reality in which the Big Bang is a local event within a larger system that has no first moment and no final one. A system that runs not because it started somewhere, but because there is no condition under which it stops. The terrifying quality of this is not that it makes the universe feel large. The universe already felt large. The terrifying quality is what it does to the concept of creation. Because if creation never occurred, if the universe is a system that has been cycling or inflating or transitioning indefinitely, then the question that the Big Bang was supposed to answer was never answered. It was dissolved. And a question that is dissolved rather than answered has not gone away. It has only become harder to ask. The universe behaves like physics. That sentence sounds obvious until you sit with it long enough to notice it isn't. Physics is a human invention, a set of mathematical descriptions developed over centuries to model what matter and energy appear to do. The fact that those descriptions work is not self-explanatory. The fact that they work with the precision they do, that the same equations govern the orbit of a planet and the behavior of an electron, that the constants embedded in those equations appear fixed across every measurement ever taken from every location ever sampled, is not something the universe was obligated to arrange. Reality did not have to be mathematically legible. It did not have to be consistent. It did not have to have rules at all. It has rules. Precise ones. Universally applicable ones. Rules that, the deeper physicists examine them, increasingly resemble something that was not discovered but specified. This is where physics stops being comfortable. The simulation hypothesis, in its popular form, is easy to dismiss. It arrives attached to science fiction aesthetics. Green cascading code, desert wastelands, Keanu Reeves in sunglasses, and the version most people encounter is essentially a thought experiment dressed as metaphysics. But the argument that underlies it is not aesthetic. It is logical, and its most rigorous form was constructed not by a novelist, but by a philosopher at Oxford. Nick Bostrom's 2003 paper does not argue that we live in a simulation. It argues that one of three propositions must be true. Either all technologically advanced civilizations go extinct before developing the capacity to run detailed simulations of conscious experience, or all such civilizations, for reasons unknown, choose not to run such simulations, or we are almost certainly living inside one. The logic is uncomfortable because it is valid. If simulations of conscious experience are eventually possible, and if any civilization ever runs many of them, then simulated minds outnumber non-simulated minds by an astronomically large ratio. And a mind that has no way of knowing whether it is simulated or not, a mind exactly like the one reading this, has no principled basis for assuming it is in the minority. The dismissal of this argument typically relies on the assumption that sufficiently detailed simulation of physical reality would require computational resources beyond any achievable scale, that the universe is simply too complex to fake. But this dismissal was made before physicists began noticing how many features of the universe resemble not brute physical reality, but optimized computational architecture. Consider the speed of light. In physics, it is the universal speed limit, the maximum velocity at which information can travel through space. Nothing has ever been observed exceeding it. Nothing in the theoretical framework permits it. The explanation offered within classical physics is relativistic. Spacetime geometry simply does not permit faster propagation. This is internally consistent. It is also precisely what you would expect if the universe were operating under a processing constraint. A simulation does not render what is not observed. A simulation does not transmit information faster than its update rate permits. The speed of light functions, in this framework, less like a feature of spacetime and more like a bandwidth ceiling. This is one parallel. There are others. Planck length is the smallest meaningful unit of spatial measurement in physics, approximately 1.6 times 10 to the negative 35th meters. Below this scale, the concept of distance loses physical meaning. Not because our instruments are insufficiently precise, because the mathematics itself breaks down at that threshold. Space below the Planck length is not small, it is undefined. This is precisely what you would expect from a reality built on discrete units. A pixelated substrate that appears smooth at observable scales, but has a resolution limit at the fundamental level. The Planck length is, in this reading, not the smallest physical distance. It is the minimum render distance, the grid spacing of the underlying structure. Then there is quantum mechanics. Quantum mechanics is the most precisely verified theory in the history of science. Its predictions have been confirmed to a degree of accuracy that has no parallel in any other scientific framework. It is also, by universal agreement among the physicists who use it daily, deeply strange. Particles exist in superposition, in multiple states simultaneously, until measurement forces a specific outcome. The probability of each outcome is determined by the wave function, a mathematical object that evolves according to precise rules, and then, at the moment of measurement, collapses into a single value. The collapse is instantaneous. It is not caused by anything within the physical system. It is caused by the act of observation itself. This is not an interpretation. This is what the mathematics predicts, and what experiment confirms. The universe, at its fundamental level, does not commit to definite states until those states are observed. Prior to observation, it maintains all possibilities simultaneously. This is not a failure of measurement. It is not that the particle secretly has a definite state that we cannot access. Bell's theorem and subsequent experiments have ruled that out conclusively. The particle genuinely does not have a definite state. Reality, at the quantum level, is potential until something interacts with it and forces an outcome. This behavior has a name in computational theory. It is called lazy evaluation. It is an optimization technique used in programming to avoid computing outputs that are not needed, to leave values undefined until the moment they are required, at which point the system calculates and returns the result. Lazy evaluation reduces processing load by not computing what is not accessed. The quantum universe behaves as though it is doing exactly this. It does not commit computational resources to definite states in regions that are not being measured. It maintains superposition, all possible states held simultaneously without collapse, until an observer forces an interaction, at which point the system returns a definite value. The parallel is not metaphorical. The behavior is formally identical. Max Tegmark, a cosmologist at MIT, has spent 2 decades constructing a framework called the mathematical universe hypothesis. Its central claim is that the universe does not merely follow mathematical laws. The universe is a mathematical structure, not described by mathematics, constituted by it. In Tegmark's framework, physical existence and mathematical existence are identical. Any mathematical structure that is internally consistent exists physically. Our universe is one such structure. The reason physics is mathematically legible is not that mathematics is an unusually good description tool. It is that there is nothing beneath the mathematics to describe. Remove the equations, and you remove the universe. The territory is the map. This framework carries a consequence that its author states plainly and that most readers take longer to absorb. If the universe is a mathematical structure, then information is not a property of the universe. Information is what the universe is made of. Matter is not fundamental. Energy is not fundamental. The substrate of reality is informational. Patterns of relationship, constraint, and structure. And what we experience as physical existence is the behavior of that informational substrate at the scale available to human perception. John Wheeler, one of the central figures of 20th century theoretical physics, the man who coined the term black hole, arrived at a similar conclusion from a different direction. In the last decades of his career, Wheeler argued for a principle he called it from bit, the proposition that every physical entity, every it, derives its existence from information, from answers to binary questions, from bits. The universe, in Wheeler's framework, is participatory. It does not exist independently of the acts of observation that extract information from it. Observation is not a passive recording of pre-existing facts. It is a constitutive act. Reality is not found. It is, in some sense, that Wheeler spent years trying to make precise, built from the questions asked of it. The disturbing quality of this line of thinking is not that it is speculative. Several of the world's most rigorous theoretical physicists have converged on variations of it from different starting points, using different mathematical tools, working within different research programs. The convergence is not a conspiracy. It is what happens when you push hard enough against the question of what physical reality is actually made of. At sufficient depth, matter dissolves into energy. Energy dissolves into fields. Fields dissolve into quantum states. Quantum states dissolve into information. And at the bottom of that descent, the question of what information is made of, what the physical substrate of the informational universe actually consists of, returns not an answer, but the same wall the Big Bang singularity returns. A point at which the explanatory framework runs out and something else would be required. The physical constants deepen the unease. The fine structure constant, which governs the strength of electromagnetic interactions, is approximately 1/137. Slightly different and atoms become impossible. The cosmological constant, which governs the rate of the universe's expansion, is tuned to a precision that physicists describe as the worst prediction in the history of physics. Theory suggests it should be 10 to the 120th power larger than it actually is, and no physical mechanism explains why it is as small as it needs to be for matter to exist. The masses of the fundamental particles, the ratios between fundamental forces, the number of spatial dimensions in which physics operates, each of these could in principle take a vast range of values. They take the values that permit complex structure to exist. the values that permit, eventually, observers. This is called fine-tuning. It has orthodox explanations: the anthropic principle, the multiverse, the possibility that a future theory will reveal why these values are natural. Each explanation is serious. None of them eliminates the observation that the universe appears configured rather than arbitrary, that its parameters sit at values that were not required, but were, in some sense, chosen. The word chosen is one that physicists use carefully and with visible discomfort. It implies an agent. It implies intent. It implies, underneath all the formal language and the careful qualifications, something that the physics alone cannot supply. What the physics can supply is the observation. The universe behaves as though it runs on rules, as though those rules were set before the running began, as though matter and energy and space-time are not the deep reality but the output, the rendered surface of something operating beneath them that has not yet been named and may not be nameable in the vocabulary physics currently has available. That is not a proof, it is a pattern. And patterns, once seen, are almost impossible to unsee. You are not reading about the universe. You are, according to several mathematically serious interpretations of quantum mechanics, participating in its existence, not metaphorically, not in the loose inspirational sense that human consciousness gives meaning to an indifferent cosmos, in the precise, formal, equation-level sense that the physical state of reality in your vicinity is not fully defined until something like you, something capable of extracting information from it, interacts with it. The universe in this reading does not exist completely and independently in the way common sense insists it must. It exists in a state of suspended possibility, and observation is the mechanism by which possibility becomes fact. This is not a fringe position. It is the unresolved core of the deepest disagreement in modern physics, and it had been unresolved for a century. Quantum mechanics does not describe what particles are. It describes what measurements of particles return. This distinction was present from the beginning of the theory and has never been dissolved by anything discovered since. The wave function, the mathematical object at the center of quantum mechanics, evolves with precise predictability until a measurement occurs. At the moment of measurement, it collapses. The superposition of all possible states resolves into one actual state. The collapse is instantaneous, is not predicted by the wave function's own evolution, and is not caused by anything that can be described within the physical system being measured. Something outside the system causes it. For a century, the question of what that something is has been the most uncomfortable question in physics and the most consistently avoided one. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, and still the version taught in most physics courses, resolves the question by refusing to answer it. The wave function collapses upon measurement. What counts as measurement is left deliberately undefined. What is happening to the particle before measurement? Whether it truly exists in superposition or merely appears to, is declared outside the scope of physics to answer. Copenhagen tells physicists how to calculate and explicitly instructs them not to ask what is happening when they are not calculating. For practical purposes, this has worked. The predictions are extraordinarily accurate. The question of what they are predictions about has been, by professional consensus, set aside. John Wheeler could not set it aside. Wheeler's delayed choice experiment is not a thought experiment. It has been performed. In multiple forms with increasing precision, the results are consistent and they do not permit comfortable interpretation. The setup is a variation on the classic double-slit experiment, in which particles are fired at a barrier with two openings. When both slits are open and no measurement is made of which slit the particle passes through, the particle produces an interference pattern on the detection screen, a pattern that can only arise if the particle passed through both slits simultaneously, as a wave. When a detector is placed at the slits to determine which one the particle used, the interference pattern vanishes. The particle behaves as a particle, passing through one slit or the other, and produces two bands rather than an interference pattern. The act of measurement changes the physical behavior of the particle. Wheeler's modification introduces the choice after the particle has already passed the barrier. The decision about whether to measure which slit information is made after the particle has, by any classical account, already committed to either wave-like or particle-like behavior. In the original thought experiment, Wheeler proposed using the light from distant quasars, introducing a delay of billions of years between emission and the observer's choice of measurement setup. The results of actual performed versions of the experiment confirm the prediction. The particle's behavior, wave or particle, is determined by a measurement choice made after the particle has already passed the point at which that behavior would, classically, have been fixed. The future measurement appears to reach backward in time and determine what the particle was doing in the past. This is not a failure of the experiment. It is the result. And it is not explicable within any framework that insists the particle had a definite state before measurement occurred. Wheeler's response to this was not to retreat, but to generalize. He proposed what he called the participatory universe. The idea that the universe is not a machine running independently of the observers it eventually produces, but a self-referential loop in which observation is constitutive of reality rather than merely revelatory of it. The universe, in Wheeler's framework, generates observers. Those observers, through acts of measurement, reach backward across cosmic time and participate in defining the universe's history. The Big Bang is not a past event that observers passively inherited. It is, in some formal sense, that Wheeler spent decades trying to make precise, partly determined by the existence of the observers who later emerge from it. The universe is not a stage on which consciousness appears. It is a system that requires consciousness to complete itself. This idea was not well received by most physicists. It remains deeply controversial. But Wheeler was not alone in following quantum mechanics toward the observer. John von Neumann, one of the most rigorous mathematical minds of the 20th century, had already produced a formal analysis of the measurement problem that pointed in the same direction. Von Neumann's analysis of the chain of physical interactions involved in any quantum measurement showed that the boundary between quantum system and classical observer, the boundary at which the wave function collapses, cannot be placed at any physical location within the chain. Every detector is itself a quantum system. Every physical interaction that constitutes measurement is itself describable by quantum mechanics and should itself be subject to superposition. The only element of the measurement process that is definitionally outside the quantum system, is the conscious observer. Von Neumann did not argue, as a metaphysical position, that consciousness causes collapse. His mathematics showed that the chain of physical causation in measurement has no natural termination point except at the observer. The conclusion was not his preference. It was where the formalism led. Eugene Wigner, a Nobel laureate and von Neumann's colleague, followed this to its most explicit statement. Wigner's friend is a thought experiment in which an observer inside a sealed laboratory measures a quantum system and records an outcome. From inside the laboratory, the measurement has occurred. The wave function has collapsed. A definite result has been obtained. From outside the laboratory, before the door opens and the result is communicated, the quantum formalism describes the entire contents of the laboratory, including the observer inside and their recorded result, as being in superposition. The observer inside the lab has a definite experience. The observer outside the lab, applying quantum mechanics consistently, must describe that experience as being in superposition. Both descriptions are formally correct within their respective frameworks. They cannot both be fully real. The conflict between them is not resolvable without making a choice about what observation actually does to reality. A choice that quantum mechanics, applied consistently, does not make for you. Recent experiments have extended Wigner's friend from thought experiment to laboratory. In 2019, a team at Heriot-Watt University implemented a version of the scenario using photons and beam splitters in place of human observers, and confirmed that the predictions of quantum mechanics in the Wigner's friend scenario are borne out, and that they are incompatible with simultaneously assuming that measurement results are real, that they are absolute, and that observers can always reach agreement about them. At least one of those three assumptions must be wrong. Which one is not determined by the experiment? The experiment only shows that you cannot keep all three. Consciousness-based interpretations of quantum mechanics are held by a minority of physicists, and the majority's skepticism has legitimate grounds. The word observer in quantum mechanics does not necessarily mean a conscious observer. Any physical system that entangles with and records information about a quantum system counts as an observer in the formal sense. Many physicists argue that the collapse of the wave function is not a mystery requiring consciousness as its explanation. It is a transition from quantum to classical behavior driven by decoherence, the process by which a quantum system interacts with its environment and loses its superposition. Decoherence is real and well documented. It explains quantitatively why macroscopic objects do not appear to be in superposition. It does not explain why any particular outcome occurs rather than another. It explains the disappearance of interference. It does not explain the selection. The selection problem, why this outcome rather than that one, remains open. The many worlds interpretation avoids it by denying that selection occurs. Every outcome happens in a branching structure of parallel universes. The measurement problem dissolves because nothing is lost. Every possibility is realized. The cost of this solution is ontological. You purchase the absence of selection by multiplying universes without limit. Whether that is a solution or a redescription of the problem depends on what you think physics is for. Relational quantum mechanics, developed by Carlo Rovelli, avoids consciousness by making quantum states observer relative. A particle's state is not absolute, but defined only relative to a specific observer, and different observers can legitimately hold different, non-contradictory descriptions of the same physical event. This framework is internally consistent. It also, as a consequence, eliminates the notion of an objective universal state. Reality becomes a network of relationships rather than a collection of facts. There is no view from nowhere. There is no description of the universe that is not somebody's description. Every available interpretation of quantum mechanics, every serious framework for understanding what the theory actually means, either requires the observer to play a constitutive role in defining physical reality, or distributes reality across an infinite number of branches, or eliminates the concept of objective physical state entirely. The version of reality that existed before quantum mechanics, solid, continuous, independent, fully real in the absence of anyone looking at it, is not available as an interpretation of the physics. It has been ruled out not by philosophical argument but by experiment. Bell's theorem and its subsequent experimental tests established definitively that the universe does not contain hidden variables that predetermine measurement outcomes. The particle does not secretly know what it is going to do before it is measured. The measurement is not a revelation. It is, at minimum, a participation. What remains contested is the depth of that participation, whether observation shapes reality at its edges or constitutes it at its core. Whether consciousness is an incidental feature of a universe that could exist equally well without it, or whether, as Wheeler's participatory universe suggests, the universe's existence in any fully realized sense requires the observers it produces. Whether you are in the universe or in some formal and terrifying sense, partly responsible for it. The experiment does not answer this. The experiment only confirms that the question cannot be avoided by anyone who takes the physics seriously. And the physics has been taken seriously enough to build every piece of technology that modern civilization runs on. The same framework that predicts transistors, lasers, and MRI machines also predicts that the universe does not fully commit to definite states in the absence of observation. Both predictions come from the same equations. Both have been confirmed. The technology works. The question of what it implies about the nature of reality has not been answered. It has only become harder to look away from. The universe is large. This is a fact that has been stated so many times, in so many contexts, with so many superlatives attached to it, that it no longer lands with the force it should. The observable universe spans approximately 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars. The numbers are so far beyond the scale at which human intuition operates that the mind encounters them, acknowledges them formally, and then quietly files them alongside other quantities it cannot actually process: national debt figures, evolutionary timescales, the number of cells in a body. Astronomically large. Yes, understood. Move on. What modern physics has produced is something that makes the observable universe feel like a footnote, not larger than we thought, not vastly larger, larger in a way that the word larger cannot carry. The frameworks that most accurately describe the early universe, The same frameworks that resolved outstanding problems in the standard Big Bang model and whose predictions have been confirmed by precision measurement of the cosmic microwave background generate infinite universes not as a speculative bonus, but as a structural requirement. Our universe is not, in these frameworks, the universe. It is an event, one local occurrence within a process so vast that the entirety of everything we can observe, every galaxy, every star, every particle in the 93 billion light-year sphere of space that constitutes the limit of our observational reach, is to the full structure of reality roughly as a single atom is to the Earth, not approximately. The ratio is worse than that. Inflationary cosmology was developed in 1980 by Alan Guth as a solution to specific problems with the standard Big Bang model. The horizon problem, the flatness problem, the absence of magnetic monopoles predicted by grand unified theories. The solution it proposed was a brief period of exponential expansion in the universe's earliest moments, during which space expanded faster than light, smoothing out the initial conditions and producing the uniform, flat universe we observe. The theory worked. Its predictions, the specific pattern of temperature fluctuations in the cosmic microwave background, were confirmed by satellite measurements to extraordinary precision. Inflation is now a standard component of modern cosmology. It is not controversial in the way that, say, string theory is controversial. It is, by the standards of the field, well supported. Inflation has a consequence that is less widely discussed than its successes. The mechanism that drives inflation, a quantum field called the inflaton, which carries enormous energy density in its early state, does not stop inflating everywhere at once. Quantum fluctuations cause different regions of the inflating space to exit the inflationary phase at different moments. The region that exits inflation in any given location becomes a bubble of non-inflating spacetime, a universe with its own physical properties, its own temperature, its own initial conditions determined by the state of the inflaton at the moment of exit. The region surrounding that bubble continues inflating and generating new bubbles. And because inflation expands space exponentially, doubling it at a rate that makes the expansion we currently observe look imperceptible, the inflating region always generates new space faster than bubbles can form within it. The process does not converge. It does not run out of space. It produces bubbles, universes, continuously without limit, in a structure that is eternal in the future direction and may be eternal in the past direction as well. This is the inflationary multiverse. It was not proposed as a philosophical speculation. It emerges directly from the mathematics of the theory that solved the horizon and flatness problems. Guth and his colleagues did not add it as a feature. They found it as a consequence. Each bubble universe is causally isolated from every other. Light cannot cross the exponentially expanding space between them in any finite time, which means no observation made from inside one bubble can ever confirm the existence of another. The multiverse is, in this specific technical sense, untestable by any instrument that could in principle be built. It is also, in the view of the physicists who develop inflationary models, almost certainly real. Because the alternative, a version of inflation that stops everywhere simultaneously, requires a level of fine-tuning that the theory was designed to eliminate. The bubbles are not identical. The physical constants in each bubble universe, the strength of gravity, the mass of the electron, the value of the cosmological constant, are determined by the specific state of the inflaton field at the moment of that bubble's exit from inflation. Quantum mechanics makes those states fundamentally random within a range. Different bubbles exit with different constants, producing different physics. Most combinations of constants produce universes that cannot form atoms, or cannot sustain nuclear reactions, or expand so rapidly that matter never gravitationally coalesces into structure of any kind. The overwhelming majority of bubble universes in the inflationary multiverse are, by any reasonable definition, sterile, empty, featureless expansions of particles that never combine into anything. The universes capable of producing stars, planets, chemistry, and observers are a vanishingly small fraction of the total. We are in one of those rare bubbles because only those rare bubbles contain anything capable of asking where it is. This is the anthropic principle applied at cosmological scale, and it is either deeply satisfying or deeply disturbing, depending on what you want physics to do. It's satisfying explains why our constants are what they are. We could not exist in a universe where they were different. So naturally, we find ourselves in one where they permit existence. It disturbs because it means the constants are not fundamental. They are not the outputs of a deep theory that will eventually explain why they must be what they are. They are accidents. Lucky draws from a distribution generated by quantum randomness across an infinite ensemble of universes. The fine-tuning that once seemed to require an explanation or a designer dissolves into statistics. But the statistics require infinity to work, and infinity is a difficult thing to require. Alongside the inflationary multiverse, quantum mechanics generates another. The many-worlds interpretation, first proposed by Hugh Everett in 1957 and developed extensively since, resolves the measurement problem. The question of why quantum superpositions collapse to definite outcomes, by denying that collapse occurs at all. In Everett's framework, the wave function never collapses. It continues to evolve according to the Schrödinger equation, always, without exception. What appears to be collapse is branching. When a quantum measurement occurs, the universe splits into a branch for each possible outcome. Both outcomes occur. Both are real. The observer in each branch has a definite experience, a single specific result, because each branch contains a distinct version of the observer. The other branches are not destroyed or made hypothetical. They continue to evolve, containing their own stars, planets, histories, and observers, causally disconnected from this branch but ontologically identical in status. The branching is not limited to deliberate laboratory measurements. Any quantum event, any interaction between particles that has multiple possible outcomes, produces a split. Quantum events are constant, occurring at the level of every atom in every material, in every region of space, at every moment. The number of branches generated per unit time by the quantum activity of the observable universe alone is not a number that can be written. It exceeds any quantity that has ever been named, and each branch is itself a universe, continuing to evolve and branch, producing its own infinite tree of further divergences. The many worlds multiverse does not merely dwarf the observable universe. It dwarfs the inflationary multiverse. It generates continuously a structure of parallel realities so vast that the word infinite undersells it, because the infinity here is not a static collection, but an endlessly proliferating process, compounding at every moment in every location. In the Everett multiverse, every quantum possibility is realized. This has a specific implication that is easy to state and almost impossible to absorb. Somewhere in the branching structure, in some world that diverged from this one at some quantum event in the remote past, every possible history that was not made impossible by the laws of physics has occurred. Not every likely history, every possible one. There are branches in which every improbable outcome of every quantum event aligned in the most favorable direction, producing consequences that in this branch we would call miraculous, and in that branch simply call history. There are branches in which the improbable alignments went the other way. There are branches in which you made every different choice available at every moment. Your choices depended on processes that, at some level, had quantum components, which is to say every moment. In the many worlds multiverse, uniqueness is not a physical category. Every version of every event that could happen does happen. This version, this branch, this history, this particular arrangement of everything is not special. It is not unique. It is one thread in a fabric of infinite threads, indistinguishable in its ontological status from every branch in which everything went differently. Then there is a third framework, arising from string theory and the physics of extra dimensions. M theory, the framework that unifies the various versions of string theory, proposes that the universe we inhabit is not three-dimensional space plus time, but a four-dimensional surface, a brain, embedded in a higher dimensional space called the bulk. Other brains exist in the bulk, parallel to ours, separated by distances measured in extra dimensions rather than the three we can access. They are, in the most literal sense, other universes, complete, self-contained realities with their own matter, forces, and physical histories. We cannot see them. Nothing that propagates through the three dimensions of our brain can reach them, but gravity can leak through the bulk. Gravity is, in string-theoretic frameworks, not confined to our brain. It propagates through higher dimensions. And if brains can interact gravitationally across the bulk, they can collide. The ekpyrotic model developed by Paul Steinhardt and Neil Turok in the early 2000s proposes that the Big Bang was not a singularity, but a collision. Two brains drifting through the bulk struck each other. The energy of the collision was deposited on both brains as heat and radiation. What we experience as the Big Bang, the hot, dense initial state of our universe and its subsequent expansion, was the after effect of that impact. The pre-collision state of our brain was not nothing. It was a cold, nearly empty brain with a long prior history. The Big Bang was not the beginning. It was a collision event in a larger structure of brains and bulk that had its own prior evolution. The ekpyrotic model makes testable predictions. It predicts a specific signature in the pattern of gravitational waves in the cosmic microwave background. A signature that differs from the signature predicted by inflationary cosmology. Current measurements have not yet achieved the sensitivity required to distinguish between them definitively. Future observatories may do so. The distinction matters enormously. One says our universe emerged from a singularity preceded by nothing. The other says it emerged from a collision preceded by another universe's history. Both are consistent with everything currently observed. What all three of these frameworks share, the inflationary multiverse, the Everett multiverse, and the brain collision picture, is the elimination of our universe's singularity, not its importance, its singularity, its status as the only one, the real one, the one that matters in a way that others do not. In each of these frameworks, generated not by speculation but by serious attempts to resolve specific problems in fundamental physics, our universe is a local event within a larger structure, an accident within an ensemble, an outcome within a distribution. The existence of everything we have ever observed or will ever observe, every particle, every force, every moment of history, is in these frameworks one entry in a list whose length is not bounded by any finite number. The list does not assign priority. It does not rank. Our universe appears on it for the same reason every other entry appears, because the physics that generates entries does not discriminate. And that absence of discrimination is not a comfort. It is the most disorienting feature of modern theoretical physics, because a reality that generates everything without preference is a reality in which the existence of this, of here, of now, of the specific arrangement of matter and history and consciousness reading these words is not the point. It is not even an especially notable data point. It is what happens when you run the physics long enough. One of the things that happens, unremarkably, inevitably, alongside everything else. Everything around you is stable. The chair, the floor, the air, the atoms composing your body and the space between them. All of it sits in a state of reliable, continuous physical existence that is not varied by any detectable measure since the moment you began reading this. The laws of physics governing the behavior of matter in your immediate vicinity are the same laws that governed it yesterday, the same laws that governed it 1 billion years ago, when the matter composing you was dispersed across the interstellar medium of an earlier galaxy. Stability is the most fundamental feature of experienced reality, so fundamental that it is not experienced as a feature at all. It is experienced as the absence of anything to notice. This is precisely the problem. Stability in physics is not a single condition. It is a spectrum. At one end sits true stability, a system at its lowest possible energy state, from which no perturbation can dislodge it, in which it will remain indefinitely. At the other end sit unstable systems. Systems perched at energy peaks from which any perturbation sends them cascading irreversibly downward. And between these two extremes lies a condition that physics calls metastability. A metastable system occupies a local energy minimum, a small valley in the energy landscape, but not the global one. It is stable against small disturbances. It will remain in its current state for an arbitrarily long time without any applied force. But the global minimum, the true lowest energy state, exists elsewhere in the landscape. And if the system ever acquires, by any mechanism, enough energy to cross the barrier between its current valley and the deeper one, it will fall irreversibly into the lower state and release the difference in energy as it does. The universe may be metastable. This is not a metaphor. It is a current, active, unresolved question in theoretical physics, and the implications of a positive answer are unlike those of any other open question in science. The Higgs field is a quantum field that permeates all of space, every point in the universe, including the points that appear to contain nothing, contains the Higgs field at a specific value, a specific energy state. This value is what gives elementary particles their mass through their interaction with the field. Without the Higgs field at its current value, electrons would be massless, atoms could not form, chemistry could not occur, and nothing resembling matter as we know it would exist. The Higgs field is not an incidental feature of particle physics. It is a structural requirement for the existence of everything that exists. In 2012, the Large Hadron Collider at CERN confirmed the existence of the Higgs boson, the particle associated with the Higgs field, and measured its mass with precision. The measurement was a triumph. It was also, to the physicists who ran the numbers afterward, deeply unsettling. The measured mass of the Higgs boson, approximately 125 gigaelectron volts, places the current value of the Higgs field in a specific region of its energy landscape. Calculations completed after the measurement indicate that this region is not the global minimum. The Higgs field, at its current value, sits in a local minimum, a metastable state. The global minimum of the Higgs field's energy landscape lies elsewhere, and the value of the Higgs field at that global minimum would correspond to a completely different physics, one in which the fundamental constants of nature are different, in which the particles that constitute matter have different masses or do not exist at all, and in which nothing resembling the universe we inhabit could exist. The calculations carry significant uncertainty. They depend on precise values of the top quark mass and the Higgs boson mass, both of which have been measured but both of which carry experimental error bars. Depending on the exact values within those ranges, the universe is either stable, metastable, or barely metastable, a condition referred to, with the particular black humor of high-energy physics, as near critical. The central values of current measurements place the universe in the metastable region. The uncertainty is not large enough to rule out true stability, but it is not large enough to confirm it either. The state of the evidence, as it currently stands, is that the universe is more likely metastable than stable. The probability is not a physical certainty. It is a calculation. And the calculation says the ground beneath reality is not the ground floor. The mechanism by which a metastable Higgs field could transition to its true minimum is quantum tunneling. Quantum tunneling is not hypothetical. It is a well-documented quantum phenomenon responsible for nuclear fusion in stars, for radioactive decay, for the operation of the transistors in every computing device in existence. A quantum system does not need to acquire the classical energy required to surmount a barrier in order to cross it. There is a non-zero probability, governed precisely by quantum mechanics, that the system will simply appear on the other side. The probability decreases exponentially with the height and width of the barrier. For the Higgs field, the barrier is large enough that the expected waiting time before a spontaneous tunneling event, before the field randomly transitions from its current metastable state to the true minimum, is estimated to be vastly longer than the current age of the universe, longer than any time scale that has practical meaning. By conventional cosmological standards, the vacuum is stable on any relevant timescale, and the risk in any given human lifetime is, for all practical purposes, zero. This would be reassuring if, for all practical purposes, were the relevant standard. The tunneling event, if it occurred, would not produce a warning. It would not produce a signal of any kind that travels ahead of it. The transition would begin at a single point in space, a quantum fluctuation, occurring randomly, anywhere in the universe. And from that point, it would expand outward at the speed of light as a bubble of true vacuum. Inside the bubble, the Higgs field has its lower energy value and physics has its different constants. The bubble wall is not a boundary that matter can interact with and survive. It is a boundary at which the laws of physics change instantaneously. On contact with the bubble wall, every particle, every atom, every nucleus, every electron ceases to be what it currently is because the rules that define what particles are no longer apply inside the bubble. The transition from metastable to true vacuum does not destroy matter in the way that an explosion destroys matter. It does not leave anything behind. It replaces the physics that defines matter with different physics. The universe inside the bubble is not a ruined universe. It is a different universe, with no memory of or physical continuity with the one that preceded it. The bubble expands at the speed of light. No signal can precede it. No observation can detect it before it arrives. The moment of its arrival is identical to the moment of impact. There is no interval between detection and consequence in which preparation could occur or warning could be issued. Everything within the bubble's expanding radius is converted instantly and without remnant. And because the bubble expands at light speed in all directions from its origin point, everything in its eventual path, however distant, however isolated, will, given enough time, be reached. A tunneling event that occurs in this galaxy ends everything here. A tunneling event that occurs 1 billion light years away ends everything here in 1 billion years from a bubble whose existence cannot be known until it arrives. There is one more element to this picture that the popular discussion of vacuum decay typically omits. The universe is not the only possible site of nucleation. A sufficiently energetic collision between particles can catalyze the transition, can provide the local energy concentration needed to initiate a bubble of true vacuum without waiting for a spontaneous quantum fluctuation. The concern expressed and then addressed when the Large Hadron Collider was first proposed was that particle collisions at the LHC might reach energies sufficient to initiate vacuum decay. The analysis concluded they would not, that cosmic rays striking planetary atmospheres routinely produce collisions at higher energies than the LHC generates, and that the universe's long history of such collisions without detectable vacuum decay events provides empirical evidence that LHC energies are insufficient to trigger the transition. The concern was assessed and set aside. The assessment was based on what is known. What is not known is whether regions of the universe with different histories, higher energy events, different particle content, different local conditions, might have already generated nucleation events that are currently propagating outward from distant points in space. The observable universe spans 46 billion light-years in radius. The full universe, if inflationary cosmology is correct, extends vastly further. A nucleation event occurring beyond our particle horizon, the boundary beyond which no light has yet had time to reach us, would be entirely invisible to any instrument and would remain so until the bubble wall arrived, at which point the distinction between visible and invisible would lose all relevance. The seventh theory shares the same register of threat, but operates through a different mechanism. Quantum gravity approaches to cosmology, including loop quantum cosmology and some formulations of string-theoretic cosmology, suggest that the Big Bang was not the universe's first energetic event, but rather the most recent one in a series. In some formulations, the pre-Bang state was itself unstable, and our universe represents not a creation, but a decay, a transition from a higher energy state to a lower one, with our entire cosmic history being the aftermath of that fall. In this framing, the universe is not moving toward eventual equilibrium. It may be undergoing a descent through energy states that has not yet reached its final level. Our current vacuum may be the second state, not the last, and the next transition, the next fall to a deeper minimum, would be as invisible, as instantaneous, and as total as the vacuum decay scenario, not the end of our universe, a transition to something else entirely, in which the universe as we know it is simply a phase that has completed. This is where the mathematics of instability has arrived. Not at a distant theoretical catastrophe irrelevant to anything within human experience, but at the recognition that the stability underwriting every moment of existence, the reliability of physics, the constancy of constants, the persistence of the rules that make matter behave as matter, is a feature of the current state, not of reality as such. It is not guaranteed by anything deeper. It holds for now because no sufficiently large fluctuation has occurred in the right location. It will hold, by every reasonable projection, for longer than human civilization can envision, but by every reasonable projection and indefinitely are not the same thing. And the difference between them, in this specific case, is the difference between a universe that continues and a universe that doesn't. The universe is not the container of reality. It may be the content. That sentence requires a moment. The intuition it disturbs is so foundational that it rarely surfaces as an assumption. It simply operates beneath every other thought, silently, as the frame within which everything else is arranged. The universe is the totality. It is the thing that contains galaxies and black holes and quantum fields and the space between them. It is the structure within which everything that exists. To say that the universe might itself exist within something else, that it might be embedded, projected, derived from, or leaking out of some larger or deeper structure, is not to make a philosophical claim about what lies beyond the universe's edge. The observable universe has no edge in the ordinary sense. The claim is stranger than that. It is the claim that the dimensionality of the universe, the very number of spatial dimensions in which physics operates, may be a derived quantity rather than a fundamental one. That what we experience as three-dimensional space plus time may be a projection from a surface that has one fewer dimension. That the universe is not the room, but the image on the wall. This is the holographic principle, and it did not originate in speculation. It originated in black holes. The information paradox, first sharpened by Stephen Hawking in the 1970s, arises from a conflict between general relativity and quantum mechanics that is specific, technical, and deeply resistant to resolution. General relativity describes black holes as regions from which nothing escapes. Quantum mechanics requires that information is never destroyed, that the quantum state of any system, however complex, is preserved in principle even if it becomes practically inaccessible. These two requirements are directly contradictory in the context of black holes. Matter falls in, carrying quantum information. The black hole radiates, Hawking radiation, and eventually evaporates. If the radiation is purely thermal, as general relativity suggests it should be, the information carried by the infalling matter is destroyed in the evaporation. Quantum mechanics says this cannot happen. General relativity says it must. The paradox is not resolvable by dismissing either theory. Both have been confirmed to extraordinary precision in their respective domains. Jacob Bekenstein's resolution attempt produced something unexpected. Working on the thermodynamics of black holes, Bekenstein showed that the entropy of a black hole, a measure of the information it contains, is proportional not to its volume, but to the area of its event horizon. This is unusual. Entropy in ordinary physical systems scales with volume. A system twice as large contains twice as much information. A black hole 4 times as wide has 4 times the surface area, not 8 times the volume, and its information scales with that surface area. The implication is that all the information describing the interior of a black hole, everything that fell in, every particle's quantum state, every piece of history, is encoded on the 2-dimensional surface that bounds it. The 3-dimensional interior is, in some formal sense, a projection of its 2-dimensional boundary. Gerard 't Hooft and Leonard Susskind extended this from black holes to the universe. If the information content of any region of space is bounded by the area of its surrounding surface, if the holographic scaling is not a quirk of black holes, but a fundamental feature of how information and geometry relate, then the universe itself obeys the same principle. Everything in the observable universe, all its matter, all its fields, all its history and structure and quantum states, can be fully encoded on the 2-dimensional boundary of that volume. Not approximately. Exactly. The 3-dimensional universe is not more fundamental than its 2-dimensional description. They are equivalent representations of the same physical reality, and neither has priority over the other. Juan Maldacena made this precise in 1997 with what is now called the ADS/CFT correspondence, a mathematical duality showing that a specific type of gravitational theory in a higher dimensional space is exactly equivalent to a quantum field theory living on that space's boundary with no gravity at all. The duality is not an approximation. It is a precise equality. Every physical event in the higher dimensional interior corresponds to an event in the lower dimensional boundary theory and vice versa. Spacetime with gravity and the additional dimension is a derived description. The boundary theory without gravity is the more fundamental one. The dimension, the depth, the volume, the space in which gravity operates is emergent. It is not there in the boundary description. It appears when you switch representations. The ADS/CFT correspondence is the most studied result in theoretical physics of the past 3 decades. It has produced tens of thousands of papers. It has been used to calculate properties of strongly coupled quantum systems with no other available method. Its mathematical structure is not in serious doubt. What remains unresolved is whether it describes our universe, which does not have the specific geometry the correspondence requires, or whether it is a precise mathematical model of a kind of universe that is informative about principles but not directly applicable to the one we inhabit. The debate is technical and ongoing. The principle it demonstrates that spacetime and the dimensions within it can be emergent consequences of a more fundamental theory without those dimensions is not in question. The emergence of space from non-spatial degrees of freedom is now a serious research program, not a metaphor. If spacetime is emergent, then the Big Bang is not the universe beginning to exist. It is a feature of spacetime's description, an event in the emergent picture that may correspond to something entirely different in the fundamental one. The singularity, the breakdown of equations at the moment of apparent creation, may not be a place where physics fails. It may be a place where the emergent description reaches its own boundary, where the projection frays at the edge because it is a projection, and the edge of a projection is not the edge of what it projects from. Behind the Big Bang, in this framework, is not nothing and not a previous universe in the same spacetime. Behind it is the structure that generates spacetime as a derived quantity. A structure we have no language for because every language we have is built in 3 dimensions. The black hole cosmology models extend this vertigo further. Lee Smolin proposed that black holes in our universe give birth to new universes, that the singularity at the center of a collapsing black hole, rather than being a terminus of physics, is a transition to a new region of spacetime that inflates into a separate universe, causally disconnected from its parent. In Smolin's cosmological natural selection framework, the physical constants of the child universe are slightly mutated from those of the parent, and universes whose constants produce more black holes therefore produce more offspring universes. Over cosmological timescales, the ensemble of universes is weighted toward parameters that maximize black hole production, which are, it turns out, close to the parameters that also permit complex chemistry and stars of sufficient longevity to produce planetary systems. The implication of this framework for our own universe is precise and vertiginous. If black holes produce universes, and if our universe was itself produced by a black hole in a parent universe, then our Big Bang is not an origin. It is a reproduction event. The singularity from which our universe expanded was the interior of a collapsing stellar mass in a parent universe that will never be observable from within ours. We exist inside what is, from an external perspective, a black hole. The entirety of our cosmic history, every galaxy, every star, every moment since the Bang, is occurring inside the event horizon of an object in a larger reality, an object whose exterior we cannot see, whose parent universe we cannot access, and whose existence our physics does not require us to posit, but does not prohibit us from concluding. The observational signature that would distinguish Smolin's framework from standard cosmology is subtle and has not yet been definitively identified. The framework makes predictions about the distribution of black hole masses and stellar parameters that are in principle testable. The tests have not been conclusive. The framework remains neither confirmed nor ruled out, inhabiting the same category as several other ideas discussed in this script, serious enough to be taken seriously, untested enough to avoid certainty in either direction. What all of these frameworks share? The holographic principle, emergent spacetime, ADS/CFT duality, black hole cosmology, is a demotion of the universe from its assumed status as the fundamental level of reality. In each case, the three-dimensional spacetime we inhabit is shown to be, or proposed to be, a derived description, a representation, a surface phenomenon generated by something that operates at a level where the concepts of space and time, as we experience them, do not yet apply. The universe does not sit inside a container, but it may sit atop a substrate, a more fundamental layer of degrees of freedom, non-spatial and non-temporal in nature, from which space, time, gravity, and the expansion we call the Big Bang all emerge as collective behaviors. This is where the physics arrives when pushed far enough, not at a simpler description, at one that is structurally deeper and phenomenologically stranger. The Big Bang, in this final framework, is not the universe beginning to exist. It is the moment at which a certain description of a more fundamental reality becomes valid, the moment at which the emergent picture switches on. What was happening before, in the substrate, at the level where space had not yet appeared, is not nothing. It is something for which physics does not yet have adequate language, because the language of physics was built inside the emergent description and cannot, without entirely new foundations, reach beneath it. There are physicists building those foundations now. They work in quantum information theory, in tensor networks, in the mathematical structure of entanglement, and how patterns of quantum entanglement between boundary degrees of freedom can give rise to the appearance of spatial geometry in the interior. The geometry of space, in the most developed of these frameworks, is not a given. It is a consequence. Specifically, it is a consequence of entanglement. The fabric of spacetime is woven from quantum correlations. Tear the entanglement, reduce it, restructure it, and the space changes. In certain formulations, space tears. In others, it simply does not exist until the entanglement that generates it is present. This means the universe is not made of space containing entangled particles. It is made of entanglement generating the appearance of space. The three dimensions in which galaxies drift and planets orbit and everything that has ever happened has happened are not the floor of reality. They are the surface of something deeper, something that existed in its own terms before the Big Bang switched the projection on. The question of what that something is, what exists at the level beneath emergent spacetime, what the degrees of freedom are that entangled to produce the appearance of the universe, what was occurring in those degrees of freedom before the emergent picture became valid, is the question that sits behind every theory discussed in this script. It is the question the Big Bang was supposed to answer. It is the question every attempt to answer the Big Bang has eventually produced again, deeper, stranger, further from anything that intuition can reach. The universe is not the container of reality. It may be what reality looks like from inside a projection, and what is doing the projecting has not yet been named. Here is what science has built: a civilization capable of measuring the temperature of light that has been traveling since 380,000 years after the universe began. A civilization capable of detecting the ripple in spacetime produced by two black holes colliding 1 billion light-years away. A civilization that split the atom, sequenced the genome, mapped the neural architecture of human thought, and sent instruments beyond the edge of the solar system that still transmit data as they move into interstellar space. The accumulation of human knowledge is not a minor achievement. It is the most improbable thing this universe has produced, matter that became organized enough to study the conditions that produced it, dust that looked back at the explosion and began to ask questions. And here is what the questions have returned. Time may not be fundamental. The most mathematically complete frameworks for unifying quantum mechanics with gravity eliminate time as a basic ingredient of reality. It emerges in these frameworks as an approximation. A useful fiction that appears at the scale of human experience, but dissolves at the deepest levels of physical description. The Wheeler-DeWitt equation, one of the leading candidates for a quantum theory of gravity, contains no time variable. The universe it describes as static. Everything that has ever happened, everything happening now, everything that will happen, exists in that equation simultaneously in a structure that does not change because change requires time, and time, at that level, is not present. The sensation of time passing, the irreversibility of experience, the difference between before and after, is real. It is just not fundamental. It is what the static structure looks like from inside a particular region of it. Space may not be fundamental either. It emerges in the holographic frameworks from entanglement. Remove the entanglement, and the space it generates disappears. The universe is not a volume containing quantum fields. It is a pattern of quantum correlations that produces the appearance of a volume. The room you are in is not, at the deepest available level of description, a room. It is a consequence, a derived output of a more fundamental accounting that operates in fewer dimensions and does not contain anything recognizable as space until a certain level of organization is reached. Matter, the stuff of which everything is composed, the electrons and quarks and bosons that constitute every physical thing, including the physical substrate of the thought reading these words, is almost certainly not fundamental. The particles are excitations of fields. The fields are geometrical features of spacetime. Spacetime is emergent. What the particles are excitations of at the level beneath emergence is not yet known. The chain of reduction that physics pursues, matter to atoms, atoms to particles, particles to fields, fields to quantum states to information, has not reached a floor. Every floor uncovered has revealed another beneath it. There is no identified point at which the reduction terminates in something that is simply, irreducibly real. There is only the next level down, and the next, and the question of whether the sequence ends or continues without termination into a structure that has no bottom. Consciousness sits somewhere in this picture at a location that physics has not determined. It interacts with the quantum world in ways that the quantum formalism does not explain. Whether it causes collapse, whether it participates in reality's structure, whether it is a feature of information processing at sufficient complexity or something that requires an account not yet available. None of this has been resolved. The question of what experience is, what it is for subjective sensation to exist inside a physical universe, remains as open as it was before the first quantum experiment was run. Physics has not approached an answer. In some formulations, physics cannot approach an answer because experience is precisely what is left out when you describe the world in terms of equations, and equations are all that physics has. And the universe itself, the totality of everything described across every section of this script, may be one of infinitely many, or a projection from a lower dimensional boundary, or a bubble in an eternally inflating medium, or the interior of a black hole in a parent universe, or one cycle in an infinite sequence of cycles, or a mathematical structure among infinitely many that exist simply because mathematical consistency is sufficient for existence. The frameworks do not agree on which of these is correct. They agree that the universe, as a singular, self-contained, fundamental reality, is the one option that the mathematics consistently refuses to support. This is where the accumulation of knowledge has arrived, not at a simpler picture, at one that is irreconcilably stranger than anything the civilization that built the instruments could have predicted when the work began. The universe does not become more legible as physics advances. It becomes less so. Each framework that resolves a problem generates structurally a deeper one. The history of cosmology is a history of answers that turned out to be questions in disguise, each more fundamental than the one it replaced. There is a word for the experience of standing at the edge of what is knowable and looking outward. It has been called awe. It has been called dread. It has been called the sublime. The confrontation with something so far beyond the scale of human experience that the mind cannot contain it and does not know whether to advance or retreat. What modern physics has produced is a version of this experience that is not available through any other means, not through art, not through religion, not through philosophy alone. The specific, precise, mathematically grounded recognition that the universe is stranger than intuition allows, not metaphorically strange, but formally, provably, measurement confirmedly strange, is something that only comes from following the physics far enough. You have followed it far enough. What you are left with is not an answer. It is the permanent alteration that comes from understanding the depth of the question. The Big Bang was not explained here. It was revealed as the surface of something for which explanation has not yet been invented. Time, space, matter, observation, existence itself. Each of these arrived in this script carrying less certainty than it carried when it entered. That is not a failure of the science. It is the science working correctly. Physics does not make reality less mysterious. Every time it advances far enough, it reveals that the mystery was deeper than the previous mystery. That the universe did not become the universe in order to be understood. That it became what it is regardless of whether anything within it ever grasped what that was. And it did not stop there. It made something that would keep asking,